force. This is the chapter where we force it. We're going to talk about force, and we're going to talk about Newton's laws of motion. I will say right off the bat, I don't care if you remember which is law 1, law 2, and law 3. Because you can look that up. That doesn't really matter. What matters is that you understand how they apply to doing the math about situations with physical objects in the physical world, and that you know how to use them. So, what is force? Object meets world. That's what it is. There are forces acting on you right now. You're largely unaware of them because they've been there your whole life. We say forces cause acceleration, and that is true. But are any of you accelerating right at the moment? Not so that I've noticed. Go ahead. Oh, okay. So there's more to it than just that. But when we see an object accelerating, we do know that there are forces acting on it. Things do not accelerate in the absence of forces. Okay, so we have field forces, contact forces. We've got some magnets traveling around. Contact forces, we said, you have to have the objects in contact. This is pushing and kicking and all that. With field forces, for instance, those magnets, those little tiny chunks of metal are emanating an invisible field. Seems almost magical. Oh, you got the good one. You got the good one. So these, I'm going to steal the good one. This is the best magnet I've got. And this is actually, my husband's a software engineer. When we got married, he had a spare room. He lost that when he moved another human into his house. And the spare room had lots of old computer stuff in it. Really good use of the space, right? Like old towers. And he tore a bunch of them apart. And the old hard drives had literal magnetic brakes on them. So it was literally a little like a brake pad, just like you would see on a car, that stopped the hard drive from spinning. Well, they're rare earth magnets, so they tend to be really powerful. If you take a look over here, oh, come on. There we go. So I'm a good, 3 centimeters above the surface, and I can pick those up. Try that. You've got the weaker magnet over there, I think. Try that with the donut magnet. See how close you have to get. Yeah, like a centimeter. So, but, you know, rare earth or cheap, probably iron nickel magnet, these things are actually emanating a force. There's a force coming out of them which is affecting objects around them. Think magnets are a pretty strong force or a pretty weak force? Well, we'll get back to that. So I'd like you all to stand up now. And I would like you, with the power of your mind, to levitate 20 centimeters off the surface. Go. No, you have to stay there. Good morning. How are you all? Anybody achieving this at home in their spare time? I've heard that if you just think hard enough, no? Well, darn it. Okay, I guess you can sit back down if none of you are capable of levitation. So disappointing. Every year I just hope that one student will say, as a matter of fact, last Saturday, hasn't happened yet. So you can't defy the field force that's acting on you. What's the field force acting on you? Duh, we all know this, Moser. We've known this forever. Gravity. So let me ask you again. Those magnets, pretty powerful?
Yes.
Why?
Because they're beating gravity.
They're beating gravity. This little tiny chunk of metal is beating gravity? Are you kidding me? I can't beat gravity. Darn it. Sorry. It's the day for knocking things off edges. So we've got field forces, we've got contact forces. Here's the part that makes everybody so happy. Forces are vectors. Oh, you know what that means? Vector analysis. La, 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 la. They're vectors. They have a magnitude, they have a direction, which means we can represent them graphically. Remember graphical vector analysis? Y'all look like I just kicked you in the shins. Force vector analysis is much, much better, trust me. Because we're not going to do the kind of high-level graphical analysis with force vectors that we did with motion vectors, but we're going to use them representatively, and you are going to do a visual graphic representation of your forces for every single problem you do in this chapter. It's impossible to do most of these problems without that, and it's sort of a fundamental underpinning piece of doing this kind of physics. Gesundheit. So we have two general categories of graphical representations of force vectors. We have force diagrams, which on the face of it sounds like this must be the thing we use. It's always a trick. And then we have free body diagrams. So a force diagram shows every single force in the situation. So I am going to take, who can I pick on? Mr. Post. I'm going to pick on you. The other thing that we do, and I'll link a little video that I made years ago that I haven't used in a number of years, but that talks about the way that we generalize objects in physics. So I'm going to draw Alec. You ready? There he is. That's Alec. When we're doing force and free body diagrams, we tend to simplify, grossly oversimplify, all the objects in a situation down to little squares, little circles. Every now and then we get really generous and we do this. Whoops. There's a person. So it's sort of a rough cylinder. This kind of goes along with that idea of Fermi estimates, that we can really grossly simplify things, and it's kind of useful. So if we go ahead and we take a student, an unnamed student, down to this very simple representation, what else is the student in contact with? So I do need an actual example, so I will go ahead and use Alec. So you're in contact with the chair. So I'm going to put the chair there. You're in contact with the desk, so I'm going to put the desk there. If we were going to get, usually we only use sort of more massive objects. We could do the air that you're in contact with, because the atmosphere is exerting, well, yeah, what the heck, let's do the atmosphere, because the atmosphere is pushing down on your head. And so we have, if we sort of expand this, you are exerting a force on the chair, and the chair is exerting a force on you, and you are exerting a force on the desk, and the desk is exerting a force on you, and the atmosphere is exerting a force on you, and you're exerting a force on it. Oh, and we could keep going, and it's going to get really ugly. Because a force diagram considers every single force, every single object in the situation. And that makes it nearly impossible to actually deal with any of them. It's too much. So what we generally do is we simplify and we draw what's called a free body diagram. So here again is our student. And we know that there's a force exerted downward on the student by gravity. There's a force exerted upward on the chair. There's a force exerted back by the desk and a force exerted by the student. Let's see. There's a force exerted by the student on the desk, which is probably actually something like that. And then there's another one that would balance that. And it gets us down to something manageable. It gets us down to something we can actually analyze. And that's enormously helpful. So when we draw a free body diagram, we draw the object in isolation, and we don't have to draw it all pretty. So actually drawing it really cool kind of complicates matters, so we typically don't. We typically draw things as little cubes or little circles or cylinders with heads. Looks like kind of a hunchback cylinder with a head. That's okay. Oh, it looks like Charlie Brown, actually, on Halloween. So we simplify things, but we have to make sure that we're positioning the object accurately. That's really important. So if we say that the object is on a flat surface, we have to we're not drawing the surface generally, but we have to have that object flat. If we say that the object is on a slanted surface, and I'll copy this and paste it, then we better have that object on a slant. If we say the object is hanging from a couple of ropes in the air, then we better, and we do generally show ropes and cables that we hang things from. Well, no, we show the forces that are exerted by the cables, but we want to make sure that we have the object positioned in a way that makes it clear what the situation is. This is really important. When you draw a free body diagram, and there was one year, I think, I guess I didn't stress this enough, and so I had people, as we got into this chapter, who were doing stuff like, well, I'm not going to show you the wrong way to do it first. They weren't doing this, which is all forces originate in the center of the object in a free body diagram. Have you heard the term center of mass? That's what we're doing. And, you know, does the reason now seem even more clear that we simplify people and make them into cubes and rough cylinders? Yeah, because we want to really simplify that and get the center of mass down to the smallest point possible. We label the magnitude of the force and the force origin. And this is where we make heavy use of those subscripts. So I'm going to say that this is the force, and you'll see F sub G. That's the force of gravity on the object. If we know the magnitude of that force, we'll put it in there. So I'll say that this is 800 newtons. It's the force of the Earth downward on this individual. I'm going to get rid of that. The floor is exerting a force upward on this individual. Now, you don't know the formal name for that yet. It's normal force, but we'll get to that, I think, in the second row. So we'll just go ahead and label it as normal force. And let's say that's, whoops, also 800 newtons. If this person is standing there and their friend is pushing on them, so let's say Matt is pushing on this person, we can actually write force of Matt. And if this is 10 newtons, maybe he's not pushing all that hard, we would label that. We want to make sure that the forces are shown acting in the correct direction. And the other big thing is this, and I didn't do a great job on this. We're not doing graphical solves here. These don't have to be perfectly to scale, but a line representing a 10 Newton force should not be the same length as a line representing an 800 Newton force. So let's see. I can't even achieve what I need to on this scale. If we've got two forces that are identical in magnitude, their lines should be equal. So it doesn't have to be perfect, like I said, but it should be reasonable because it helps you visually recognize what's going on. When we have vectors to resolve, when we have a force acting on an object like this, and a force like that, and a force like that, and a force like that, can we find the net force on that object? You bet your butt we can. And we'll spend a lot of time doing that. And in order to do that vector resolution, we're not going to do any of the math today, but I'm going to have you start practicing some free body diagrams. So if you look at the chapter plan, there should be a few assigned problems under free body diagrams. And I'm going to cut you loose with the time you've got left. You can work on ping pong catapult stuff. You can work on free body diagram problems. You can think deep thoughts about cats pushing things off, or magnets if you're done with everything else. And if you need to do any more testing, the target's there.